My name is Andres Freund. I work on for Enterprise DB, and I just spent my time developing Postgres. And I spent a lot of time around performance and scalability, but also on other features. But here I want to talk about the performance aspects of how Postgres stores data, how the kernel, like Linux kernel specifically influences that, and what the problems are and what you can do to fix those problems. And also a bit about how, if you hit some of those problems, you can work around hitting them without having to wait for development. For that, we first need a tiny bit, or a bit of explanation of how Postgres works, because otherwise none of it's going to make sense. Here is basically a very small overview of how Postgres stores, like how it's like the memory management of Postgres is done. Every user connection is his own process, and to coordinate data between different processes and Postgres' own background worker infrastructure and so on, it uses shared memory. And inside that shared memory is the part of that is the Postgres' buffer cache, which is basically a cache over the disk layout of Postgres, so it doesn't have to always hit disk. And that's also very crucial for correctness issues. And attached to that is Postmaster, which is like the Postgres supervisor process, then a lot of user connections, depending on how many client connections are established to Postgres, and then there's a number of background processes that are part of Postgres. And I'm going to explain a bit what those are. And to execute, the way I/O is done is basically that it's a relatively low-level part of the stack. When a table or also an index wants to access data, and it's one of the built-in methods, then it asks the Postgres buffer manager. The buffer manager checks whether within the buffer pool whether the page is already cached, and if so, then we can directly use that data, and we don't have to hit disk, we don't have to hit the operating system, and we're good. But if it's not in there, or if you want to write the data from the buffers back to the operating system, then we ask the Postgres storage manager, and at the moment there's only one storage manager in normal Postgres, to either read that data or write it back. And that usually then actually doesn't directly hit the disk. It instead asks the operating system to either read the data or write the data. And the operating system, we use an interface to the operating system that allows the operating system to perform its own caching. And that means that first we hit the page cache. And the page cache in most operating systems depends on, the size of it depends on how much free memory you have. That is, even if you have a shared buffer setting in Postgres, which determines the size of the Postgres' own cache, of say like a gigabyte, but your database is bigger, if you have enough memory, it might still, after a while, be completely memory resident because the operating system caches all of it. And only if we don't hit the page cache, then the operating system for us is going to hit the disk. And if we write data, then we usually only write it to the page cache, and then the operating system at a later time decides to write the data from the page cache back to disk. And sometimes we tell the operating system, you need to now write it back right now because we need to rely on the data being there. For example, if you do a commit after you've inserted, we need to make sure that the write-ahead log is actually durable, because if it weren't durable and just in the cache, if you crashed afterwards, you would obviously lose all of that data. For all of this, there's so if I want to talk about I/O and performance and so on, I think there's different aspects of performance that we can talk about when in the context of Postgres. You can talk about, for example, that it's just the amount of time till I/O has finished. That is, if you do a read syscall or into the ask the Postgres buffer cache, is the data there? How long does it take till you get the data back? But that's not everything, because you might be able to do that very, very fast by using an inordinate, like an extreme amount of CPU. For example, a lot of drives these days, like the SSDs, have a mode that is called polling, where you don't actually allow the operating system CPU or you to do other work while you wait for the read. Instead, it literally just checks all the time whether the response is there. which makes it faster, but also means that you basically need 100% of the CPU while doing so, which is rarely a good answer if you have like a lot of different connections, because then they will all just waste CPU by waiting for the data. And instead, they could actually compute the query result for another connection. You can also consider that performance might be that if you execute like a read or a write, how long does it take till you get it back? But also, can you do, while you wait for the I/O to finish, can you do something else? Because quite often it's actually possible we have enough data to compute other parts of the system that, or the query that doesn't depend on the read that we just issued. So we could, for example, issue like 10 reads in parallel and get the data back quicker over all of those 10, even if it takes longer to compute the result of get the result for the first read. And then there's also that we might be able to issue I/Os in ways that are more efficient for the drive. For example, if you compare issuing a lot of writes to parts of the file that are completely randomly distributed, it will take a lot longer than if you issue those writes in the order they are laid out on the disk. And especially if all of those are like, if all the writes are contiguous, you can see, even on an SSD, you can have an order of magnitude performance difference between randomly writing data and writing the data sequentially. And you also make the SSD live longer, because random writes that are relatively small actually cost SSD lifetime, because it has to remap the data, because it only can write data in like 64 kilobyte chunks, or depending on which type of drive you're talking about. And that makes it problematic if you write a lot of random data. So what part of the subprocesses that we earlier saw does what? We have the backends, and that's just the client connection for normal queries. That is, there's one backend for every client connection that is established to Postgres, and sometimes these client connections spawn their additional backends to execute query, because we have parallelism. The parallelism starts worker backends, and they help compute the query result, but they all belong to a single client connection. There's also the checkpointer, which basically has to write out all the dirty data in the page cache every checkpoint timeout once, because then that allows us to remove all the old write-ahead log, and so we can free up disk space. Otherwise, if we didn't do that, then you could never remove write-ahead log, and if you crashed, then you would have to reprocess all the write-ahead log since the beginning of the database, and that's obviously not feasible for most workloads. It has the property that since, I think, 9.6 or 9.5, it sorts all the data in the buffer pool before writing it out to disk. And that means most of the writes are sequential, but potentially there's like gaps in the file because we haven't actually modified parts of it. Then there's also the background writer, which, and the task of the background writer is to write out dirty data so that when backend needs new space in the buffer pool, for example, because it needs to read additional data, that it has free space in the buffer pool that it can put that data in. And it's only needed if the data doesn't actually fit all in shared buffers. Because if there's enough space in shared buffers to contain all of your working set, then you don't need to actually write out any data except for a checkpoint time. And so this one only plays a role if your working set is bigger than shared buffers. And then there's, lastly, the write-ahead log writer, the wall writer, that just tries to write out the write-ahead log that other back connections write, and it tries to do so ahead of time. And it usually only does real work if you have either long-lived transactions, or if you have synchronous commit off, because every time you commit or certain other operations, the write-ahead log up to that point has to be written out. So if you have synchronous commit, there's nothing forcing equals off, then there's nothing forcing data to be written out at commit time, so the wall writer will do all of the work. What type of properties have these different type of processes. Backends usually issue a lot of random reads, or sometimes also sequential reads, because either they will hit shared buffers or they will have a cache miss and have to read the data from disk. And except for sequential scans, and most people don't have huge sequential scans, most of those reads are roughly random. There's some optimizations like bitmap scans, which order the reads roughly in disk order, but besides that, most of the reads will be random because you have index lookups and so on. And they write a write-ahead log into the pre-allocated write-ahead log files, and that's mostly sequential I/O, even though the sequentialness is distributed across all the backends because there's only one write-ahead log for all the connections. Then there's the checkpointer, which only does sequential writes, or sequential writes with gaps, and at the end it has to fsync all the data, and the background writer, which mostly issues random I/O because it just tries to free some space in shared buffers, and that will just be a random victim buffer, and I'll explain a bit more about that in a bit. And that usually means it's random, which means it's also a slower write than checkpointer, which means that you normally, if you can, your workload allows it, you want most of your writes to be done by checkpointer. And the write-ahead log writer mostly is sequential and sometimes does fsyncs.
The background writer, do you control the timing of that, or is that just based on the amount of memory, buffer, cache, things like that?
I don't quite know what you mean. The question was whether one can control the timing of the.
When it chooses to
I should repeat the questions for the video. That's why I was repeating it. Whether one can control the timing of all the work. The way it currently works is that it does writes whenever it sees that backends need new data, and then like new victim buffers to place data in, and then it tries to keep pace with that, and then so it's usage dependent. So if you never need actually data, then it will not do new buffers, then it will not do much. The problem is, I'm going to talk about that in a second, that it doesn't work all that well. But ask me again if in like 5 slides or something, it's still there. Please also just ask questions whenever. So what are the problems? I think the biggest problem is probably around reads in PostgreSQL. And one of the issues is that Postgres doesn't do a lot of prefetching of data. For example, if you do an index scan, a normal index scan, it will not prefetch multiple blocks from the disk at the same time before actually needing it, which means that we'll always wait for every single read. We have to wait before we can continue processing, unless the operating system or Postgres buffer cache has that data already cached. And that's partially a problem because our executor doesn't provide a lot of support for doing some of the necessary work to do multiple IOs in parallel, but also a problem of that we don't have the infrastructure to issue all of these prefetches that in a way that Postgres needs. And the related problem is that we at the moment don't do any concurrent IO. Except for bitmap heap scans, which you can see in the explain plan, we only ever issue one IO at a time and then wait for the result. And that's really bad for modern SSDs because a modern SSD can compute the results of like a couple hundred read requests in parallel because it's basically just a bunch of like very small SSDs bunched together, and each of these smaller chips can like compute the result of or fetch the result of a read at the same time, and the same for writes. And you can kind of work around that problem by buying very fast disks that have very low latency. This problem is really bad if you have a rotational disk, as in like an old school disk that has something turning inside, because there a random read takes anywhere from like 7 milliseconds to 15 milliseconds, which means during 15 milliseconds you will not do anything if you need that data, which obviously is a long time. Whereas if you have a modern SSD that is attached directly without going through SATA, the latencies are in the 10 microsecond range, and that's obviously a lot faster. There's still problems with that I'll come to in a second, but it's not much less bad. But it does mean that you need directly attached SSDs. If you instead have SSDs that are in like Google Cloud or AWS or something that are over the network, then you still have latency because the network takes time, because it turns out light is actually not that fast. It's true. So what do I mean by all these synchronous reads? If you imagine a query that is coming up from a client to Postgres, and Postgres has all the data necessary to answer the query is not in Postgres' cache. What does it have to do? It has first, it discovers that it needs the block, then it will ask the operating system for the data. The operating system doesn't have it cached either, so it has to ask the disk. The disk will work a bit and then return the data to the operating system, and the operating system will return it to Postgres. And then Postgres might need multiple reads to answer a query, because, for example, you might walk through all levels of an index, or you might just have a where clause that evaluates to false, so it can't return the query immediately. Or you do an aggregate over a lot of data, or. So that way we go up, down, up, down, up, down, up, down. And only at some point we have figured out that we have parts of the query computed that we can return, so we send it back. While just after we send it on the network, we can continue computing the rest of the query unless the network buffers are all full. So we do the same thing, go up and down and send queries back, and at some point we're done. But you can see that we only ever have one I/O happening at a time, because we can only, once between issuing here and getting the results, what happens is that we have called the read syscall, and the read syscall just waits till it gets the query result back. And that obviously, you can't do anything while that's happening. So if you instead have an interface that allows you to do multiple I/Os, you can get something like this pattern. For example, if after the client has sent the query, we know that we might need to read multiple blocks at the same time. So you can send read requests for all of those at the same time to the operating system. The operating system can discover that it has all the data. It doesn't have any data cached itself, so it has to send it in disk. But as I said, modern disks can compute multiple reads at the same time. So it sends 4, or arbitrary number, depending on how good your disk is and so on, and how much data we know that we need, because sometimes if you do an index scan, we don't know which blocks we might need because we have to walk through the index. And then that's sent back to Postgres. There we might discover we actually need more data, so we do this whole thing again. And then we might have enough data to return it to the client, but then to compute the next results, we can do again multiple reads in parallel. And as you can see, even though the time spent answering from the disk is roughly the same for individual reads, or it might even be slightly longer, the total time is much shorter because we can do work in parallel. And if you compare that to the case where we can only do one read at a time, but the operating system has all the data cached, it looks like this. We go to Postgres, ask the operating system, but the operating system has it cached, back and forth, and so it's much faster because the operating system has it cached. And that's why, for a long time, people have said it's good enough if we rely on operating system caching. But it turns out that this back and forth is also still pretty expensive, and with all the security fixes for processors in the last 2 years or something, this transition from Postgres to the operating system has gotten, like what's called a syscall, has gotten more expensive by, I think, a factor of like 400 or something. Like it's drastically slower to ask the operating system to do any work on your behalf, because they have to do all this work to work around the security issues. That might at some point get less bad if Intel releases new CPUs that fix all of these, or if you use CPUs that are not Intel and doesn't have these problems, but at the moment that has gotten a lot worse. So that's another reason why it might be worthwhile now to improve things. And the other one is that we now have a lot of storage devices that are much more efficient in computing query results in parallel, reads and writes in parallel. And then if you compare all of that to the case where the Postgres buffer pool is actually large enough and has all the necessary data, then obviously you'll get the query results much faster because there's no need to go back and forth between Postgres and the operating system because all of the data is in Postgres' own cache. And we always have to do the work of looking in Postgres' cache anyway. So it can, with few exceptions, not really ever be slower if you have data in shared buffers than if you have to ask the operating system. So I think the takeaway from what we have to do about this is that we have to support reads where we can issue multiple reads at the same time. And that unfortunately requires operating systems interfaces that are called sometimes like asynchronous reads, because you can issue the reads and then do something else until you get the result back. And the problem with that is that there's no good platform interface to do that. Every single operating system has a different interface, and most operating systems have like at least 2 or 3 different ways to do that. And most of the time, they're all terrible and have very bad trade-offs. In Linux, for example, you cannot, if you do asynchronous reads until very, very recently, you could not do that and still rely on the kernel page cache because that just wasn't supported. And if you did that, if you try to do that, then it would just convert all the asynchronous reads to synchronous reads without telling you that that happens, except that you get your results much, much slower. It turns out that in version 5.0, I think, of the Linux kernel, which is like, I don't know, 6 months ago or something, Linux has a new interface that actually supports doing asynchronous I/O for buffered reads too, which would allow us to more easily adapt that. And a bit later, we'll talk about the trade-off of using direct I/O, which bypasses the kernel page cache versus using the page cache. Converting Postgres to that is unfortunately a lot of work because there's some historical issues in how Postgres' I/O infrastructure worked because nobody ever wanted to add that, and some of it is a bit hard to understand why it is like it is, but we have to change a lot of things to make it work. I have started to work on that, and a few people in the community have started to work together with the Linux developers to make it faster, and I think we have a chance of using that and being a lot faster. The question still is how willing are we to be very operating system dependent, because as I said, none of those interfaces are cross-platform, which means you have to, for every platform that you want to support, you have to do substantial work. In my personal opinion, it's fine to just add support for Linux, and then whoever is interested can add support for the next platform, but I'm very sure that not everyone will agree with me. And the second part that's needed for that is that in more parts of Postgres, we have to be able to issue multiple requests to the disk or the operating system in parallel. And that means we have to figure out which blocks are we going to need next. And for most places, that's not very hard. For sequential scans, that's obviously trivial. But even for index scans, you can do that in a lot of cases. But you have to modify different parts of Postgres. And every time you have to do work. So it's a lot of relatively small chunks of work, but it still totals something substantial. Sure, we can provide more general helpers for that, but the solution of how you can to know which blocks to prefetch depends a lot on what you do. Like if you do a B-tree scan, then you can figure out in the B-tree, depending on what your scan keys are, that you need all of the lower level pages for one intermediate node, but that requires knowledge about how the B-tree looks like. We already have prefetching for the bitmap heap scan, but that relies on knowing details about how the prefetching works. So I think it's basically that. We just have to do that in more places. I don't think there's a fundamental generic infrastructure for that. What you can do is have infrastructure for controlling of how far ahead we try to read data, which at the moment is hard-coded inside the bitmap code, for example, bitmap heap scan, because that's the only place where we currently need it, but that part we should generalize, like knowing how far ahead of the current processing point to read, but that's, I think, all of it. The second biggest problem, I think, is the background writer. And as I said before, the task of the background writer is to write data back to the operating system so that when a backend needs to read new data, that it can use an existing page in the buffer pool to read that data into. And if the background worker doesn't do its work, what instead has to happen is that the backend has to look at the page and see, oh, it's dirty, it already has content, but it's modified and different from the disk contents. So it has to first write that data out, wait for that to happen, and then it can replace the contents, which then obviously mean that every query that has to do that will be delayed. And the biggest problem around the background writer that we currently have is that it doesn't actually often know which data blocks to write out. And to understand that, I have to briefly explain how Postgres chooses which pages to write out. And the Postgres algorithm for that is called the clock sweep. If you imagine that each of those buffers here is one of the pages in Postgres page cache, in this case, there are 35. I'm not sure it's actually 35, but then there's an imaginary clock hand that points at one of those pages, and say at the beginning it points to the buffer number 2, and that buffer number 2 is associated with a specific block on disk, or within a table and so on. And for each of those, we have a count that says how recently has it been used. And then when we look at the page, we see at the moment we have a usage count of 4, which just means it has been referenced 4 times since a certain point. And if the count is bigger than 0, then we can't replace the contents. So what we do is, if we need a new page, we look at that, see that the count is 4, we see that it's not 0, and then decrement the number to 3, and because we now decremented it, we look at the next page, and so on, and so on. At some point, we might encounter a page that actually is 0, and say, OK, this page has not been used very recently because it's 0, because since the last time I went around, nobody has actually used it, so I can be fairly sure that it is not very recently used. There's some problems in that logic, but that's the way it works. And then it can throw the old contents out and replace it with new contents. The problem is that the background writer, it basically just walks ahead of there and tries to find a block that is actually has a usage count of 0, because it thinks that's the only one that can be replaced very soon. But if there is none that is 0, because all of them have been used, then it doesn't write any data out. It has to wait till backends get around and do this clock sweep thing to reduce buffers usage counts to 0, and only then can it write out data. The problem is that for that to happen, the backends have to do a lot of work, and they also always have to write out data to disk, because once they find a block with 0, they will have to write it out. And that just doesn't work very well. There's also the problem that all of the I/O that the background writer does is synchronous, but it does just write into the kernel page cache. So the kernel can provide some of the asynchronicity, but we still have to synchronously go back and forth to the kernel multiple times, once for each page. And that leads to the background writer often not being able to keep up. And as I said before, usually that means the way it searches for victim buffers implies that the I/O is very random between one page and the next page, because we'll just find something that is only close by in the sense of where it's put into the buffer pool and which pages haven't been recently used. And that's bad. And one of the reasons why we can't at the moment do something like, if we write out one page and then we also look at the neighboring pages to see whether we can write them out at the same time, which takes roughly the same amount of time of just doing one write, is that we use a hash table to map the position in the table, like the table name and the position in the table, to the buffer blocks. So there's no efficient way to be able to say, what is the next, is there a dirty page adjacent to the one that we're currently writing out? Because there's no ordering within a hash table. So you have to do full lookups through the hash table whenever you want to determine that. And we haven't done that because that is too expensive. The consequence of this is that backends in a typical workload do a lot of I/O themselves. And it does so in a purely random way, and which then means that you get a lot of delays in queries. But the delay in how fast queries respond depend on whether currently the background writer finds something to write out. And as long as it finds something to write, the query response times might be OK. But as soon as it hits this case where it doesn't find anything to replace because they're all victim usage counts above 0, then the backend starts to suddenly write. And then that leads to very high latency differences, what we often call jitter between queries. And so if you see that you have unpredictable query response times, this might be responsible for that. What can you do to work around that as long as you haven't actually fixed all of this? One thing to do is you can make the background writer more aggressive. The defaults for the background writer are not sufficient for any database that actually does a fair amount of I/O. And the most important part is that thing that you need to do is to reduce the background writer delay. And you can often reduce it by like a factor of 100 to get somewhere where it actually has any chance to be able to keep up. The other things that you can do is to just increase the size of shared buffers. If you, by default, the default size of shared buffers is fairly small, which means that we constantly will have to do this buffer replacement, but you might be able to set it to a lot larger because memory is not that expensive these days. It obviously depends a lot on how large your database is and how much memory you have available. If your database is 10 terabytes and you already have 2 terabytes of shared buffers, then obviously it's not really feasible to just increase shared buffers further. And what you also can do is decrease checkpoint timeout. That has a lot of other downsides, but if you decrease it, that means that the checkpoint more often sequentially writes out all the data, and that's a lot faster than doing it in random. So that sometimes can be the least bad approach. And what you also can do is to turn on backend flush after. That will actually make writes by backends more expensive, but it will make the performance of how long it takes to do those writes a lot more predictable. A bit more about that later. What can we do to fix all of this? We can make the clock sweep also be performed inside backends. That is, inside the background writer. And that way, we can be more certain that the background writer actually finds data to work with. The other problem is that at the moment, the background writer how fast it should go is very complicated logic. It tries to measure averages of how much backends have to actually need, like how many buffers they have actually replaced in the last certain time, and it barely ever works. And the easier fix for that is to just have a queue of buffers that are clean, that can be replaced, and whenever a backend needs that, then it can just go and use that. We can also make asynchronous writes and write back as soon as you have a framework that can do multiple writes at the same time. And we can do write combining. That is, if we write out one page, we can look at the neighboring pages to whether they're also dirty. I have a prototype that implements the first two, and the results for that are pretty promising. Unfortunately, the stats didn't quite fit on here. This is for PGBench, that is TPC-like workload that does a lot of data modifications. Base, the green one is the old background writer. The red one is the new background writer. And you can see that the transaction per second with the new one is considerably higher, and especially after a certain amount of time. At the beginning, it's more, they're closer together, and the performance a lot higher. That is because the database here was just started, and that is before the first checkpoint in the database starts. And late after this, it doesn't just have to do the writes necessary to do all the queries, but it also has to perform the checkpoint in the background, which is why you see this drastic performance difference around this point in time. And you can also see that the latency and the standard deviation of the latency with the new background writer is a lot smaller, and it's more predictable, which is what the standard deviation indicates. But you can still see that there's still a lot of variation of how long it takes to perform a full transaction, and that is because it only fixes some of the issues, not all of them. And I hope to get this into Postgres 13. If somebody wants to help me, please speak up, or pick up the patch from the Git repo. So the related problem to the background writer being too slow is that the backends have to do more work writing out data, and there's some problems that are inside that part that are specific to backends doing write back, and we can improve that even because it will sometimes happen even if if the background worker is more efficient. And some sources of the problem with the backends doing write back at the moment is that you don't know whether it will, or because it will only sometimes happen, your queries will have a very unpredictable latency. Sometimes it will happen, the query will be very fast because it doesn't have to write out anything. Sometimes it will be very slow because it suddenly has to write out 100 buffers, that is 8 megabytes of data or something, before it can actually return the query, which if you have like 1,000 queries a second, 100,000 queries a second, obviously will make performance differences. And another problem is that the time of individual writes actually differs a lot, because the way the page cache is implemented in operating systems is that if you write and there's not a lot of dirty data inside the kernel page cache, it will just cache it, will just put it into the kernel page cache as dirty and then immediately return, which means the cost of that is basically one syscall and a bit of copying into the kernel page cache. But if there's already a lot of dirty data, the kernel says, hey, you already wrote a lot. What I'm going to do is, before returning, I'm first going to write out a lot of data to disk. And that might take a long time. In older versions of both Postgres and Linux, that you could end up with individual writes here taking hundreds of seconds, because the kernel had cached tens of gigabytes of data inside the kernel page cache, and then at a single write decided, before I can add more dirty data, I have to write out all of that. Obviously, that is terrible, which is why we now try to force the kernel to write back data more frequently, but you still can run into this problem, especially if you have like other applications that also run on the same server. How can you diagnose a lot of these problems? I think the best way is that you either use pgstat statements, and if you turn on, there's also a Postgres setting called track IO timing, which you should enable on all servers. And if you have enabled that, you can look in pgstat statements, and there's the block write time, and that measures just the CPU time in total of how long it takes for that query to write out data. And if you have a query that you should not cause a lot of I/O, for example, because it's a select, and it spends hundreds of seconds in total doing I/O, write I/O, then you know I probably have this problem, and I might want to do something about it. If you do explain and you add the buffers keyword, then it will tell you how many buffers it read from disk, how many buffers it hit in the Postgres page cache, and how many pages it wrote out to the operating system. And that can be very useful in general to optimize queries, but also specifically to see whether you can end up often doing writes inside read-only queries. The typical workarounds are that you make, as I said before, the background writer to be more aggressive, and that you set the setting back and flush after to something that is not 0, which is the default at the moment, and that causes that Postgres to force the kernel to write out all dirty data that the specific backend has written, and it does so after the number of kilobytes, megabytes that you set this to. And that leads to the write performance to be more predictable because there's a maximum of how much dirty data there is. And that can make a huge difference. And the real solution is obviously a new background writer. How much time do we have? A related problem is generally that at the moment the query performance can be unpredictable. It's not just due to the write back in individual connections. It's also that the kernel generally might at some random points decide to write all the dirty data back. And that might then mean that if you have concurrently a read query that you need immediately to, before you can continue computing a query, it might have to wait a long time. There's also that Postgres sometimes has certain points where it just issues a lot of I/O, and that can actually just overwhelm the I/O subsystem, and then every read query will take a lot longer. You can sometimes fix that by setting backend flush after and set all of the other flush after ones settings to smaller values. And one that might be surprising is that you can get a lot more predictable performance by disabling kernel read ahead if you don't have a lot of sequential scans, or if you have sequential scans but assume that they're all cached, because it turns out that the kernel read ahead will just make individual reads occasionally much, much bigger, and it's much slower to do read ahead for, I think the maximum is like 16 megabytes at a time than if you just do an 8 kilobyte read. And the kernel will just make individual reads much bigger to perform the read ahead, which then obviously can cause slowdowns. Here is again, pgbench workload, and here the green one is with backend flushing disabled, and the red one is with forcing all backend writes to be limited to at most 2 megabytes per backend before you force the kernel to write out all the data. As you can see, the green one has a lot higher peaks where it's a lot faster, and that is because it just writes out all the data in the kernel without any pacing as fast as possible. But at some point, like for example here, the kernel sees, hey, I have so much dirty data, I have to write it back. Then performance completely tanks. And once it has written out enough data, performance goes up. That is fine for some workloads. If you're just throughput oriented, that might actually be okay, because it doesn't matter whether row 1 million to 1.5 million of your 1 billion rows that you load a bit slower than the next 500,000. That doesn't really matter. But if you have actually users interacting with the system, or you have other latency guarantees, then that's obviously bad. And if you set backend flush after, you'll get performance that doesn't have as high peaks, but it'll a lot more predictable. But you can still see that we have some problems here, and that's where a checkpoint ends. Here's another checkpoint that ends. Here's another checkpoint that ends, and that can still be problematic. You can make these slowdowns here slower by or less impactful by turning on wall compression, because they are usually triggered by having to write a lot of full page writes after a checkpoint. If you just look at the comparison between those two settings here, you can see that the total performance, like how much the throughput of the system, is basically unchanged. The lines are basically you can't distinguish them. But the difference is just that the performance is more predictable. You sometimes might actually want that if you have very short, intermittent writes, because then them being faster is fine, because the next writes will happen in the background and you're not affected by it. So why do we want buffered I/O? And one of them reasons for that is that Postgres just has done that historically, that it's actually hard to do all of this across different platforms, not using buffered I/O. But I think the most important is that it does not need as much tuning. If you don't use the kernel page cache, every single read, every single write that is not going through Postgres' buffer cache will go directly to disk and will take a long time. That means if your shared buffer setting is not tuned appropriately to your workload, you will run into trouble. But most people don't have the time or knowledge to tune their shared buffer setting, for example, very accurately. Or they might have more databases on a system so that shared buffers cannot be tuned optimally because all of the databases together would need so much shared buffers that it's not possible, like because you would not run out of memory. And with buffered I/O, that's fine because the kernel will just do all the caching for us, or it will be a bit slower, but it's fine. You don't need to tune Postgres as accurately. But if you want to use direct I/O, you need to do a lot more tuning. The consequence at the moment for that is that at the moment Postgres defaults to 128 megabytes of shared buffers. You might want to tune that to something higher, but as long as you don't have a lot of writes, it will often be OK. Why do you want to use direct I/O? It is much faster. In real, you can just do a lot more writes in total than you can do with buffered I/O. The CPU overhead, the I/O in the operating system is like an order of magnitude or two lower when using direct I/O than compared to using buffered I/O. And it turns out that in Linux, there can only be one buffered I/O app being started at this time. There's an exclusive lock while doing writes on all file systems, which means if you have many processes doing writes at the same time, it will literally block each other. They're trying to fix that, but at the moment, that is the case. That means if you have a lot of concurrency, it really is bad. You can't have all this parallel reading, parallel writing without using direct I/O in a lot of platforms because they don't support using asynchronous reads and writes without using direct I/O for historical reasons. And I think the last issue is that when you use direct I/O, there's no issue with having double buffering because the way currently Postgres uses buffered I/O is you can end up with having data both in the Postgres page cache and in the kernel page cache. And that is wasting memory that you could use more efficiently to store other data. But there's no good way at the moment to control that, which means you will often waste memory. The rest is not that important. Cool. Any questions?
So is it safe to say that direct I/O is really only good for heavy write-loaded system, or is that not?
No, even for reads, especially you can just have more reads gone. The question was whether direct I/O is only good for write-heavy systems. And no, I would not say so. It's also good for read-heavy systems or systems that have both intermixed because you can just do a lot more reads per second if you use direct I/O than you use buffered I/O, especially if you have writes and reads at the same time. In Linux, you can't do initiate reads while you also initiate writes at the same time because there's this exclusive lock that I mentioned earlier. So yes, it's good for both. I mean, it's all cluster-wide. The question was whether the plan is to have multiple readers or writers if you use direct I/O. I'm not sure yet because you're able to issue so many reads and writes in parallel with the asynchronous interfaces that come with implementing direct I/O. It's actually possible to saturate most systems with just one process because you can issue 1,000 writes in parallel, and the storage system is not going to be able to handle that anyway. There is cases where that's not good enough. For example, if you enable checksums, that process still needs to do checksum computation, and that might be where we want to have multiple writers. I'm not sure yet whether we are going to need multiple writers. I don't think we're ever going to need multiple readers because we probably just want to do that from within the backend that needs the data and do it so asynchronously because it has higher cache locality and needs less context switches.
Obviously, if you're doing all this work, it begs the question about the kernel itself. Why doesn't the kernel allow that? Are you going to be enhancing the Linux kernel, or are you going to be enhancing Postgres?
Both. I think it's basically impossible to be as fast for buffered I/O as you are for direct I/O, but also the buffered I/O in the kernel is really bad. Yeah. So I think there's use cases for improving both. And I was at the Linux kernel developer conference like the last 3 days, and we already made quite a bit of progress on that. And I think we just need to engage a lot more with the community there because they don't really know what our problem is. Okay.
Sorry, can I ask another one? Where do we stand on the persistent memory?
I think, do you still have time to answer the question? The question was whether how we stand on system memory. I don't quite. Persistent memory. I don't think we can basically just use it as a file system using Linux's DAX mode, which basically just is a very fast file system. You can do that. We could also use it more directly to avoid the need for full page writes, especially, because you can actually rely on avoiding torn pages that way. I don't think we have done anything, but I'm not sure that it's that crucial to work on because the systems are still so hard to get, and it looks like that will be the case for another 2 or 3 years, that I'm not sure it's the most important thing to work on. But thank you.